Let's show. All right, go ahead.
Okay, awesome. So, yeah, thanks for having me here this week. I already learned a lot through all of our interesting discussions. So, I'm going to talk about something which originally I actually wasn't intending to talk about, but then somehow Thomas Ulrich asked me to find a topic that's somehow more closely related to EA or small x physics. And so in retrospect, that was actually great. So I'm going to be talking about forward digest production in CGC, because it really gave me the chance to look at some of the things that I had been doing on this over the course of the years, but then somehow got a little bit lost. So part of this is based on working collaboration with the Kansas guys, and so this is very much going to be sort of a phenomenological thought on someone trying to compute digest cross sections in CGC. So let me start with sort of a little bit of motivation, right? Since this is a phenomenological thought, right? Really, I mean, what are we after here, right? Is we want to search for nuance saturation or nonlinear effects, right? At small x, right? And so, okay, so I mean, there's a couple of things that in principle we would like to see, right? So one of them is, well, we want to see nonlinearities, which can potentially occur either in the evolution, right? Or they could also be nonlinearities in the interaction of a probe directly with the target, right? So this would nothing be tied to evolution, right? And so ideally, we would somehow like to see the emergence of a semi-hard scale QS, right? I mean, this is, I think, what we should be aiming for. Now, how can we do this? Well, okay, I mean, at some point down the road, right, we're going to hopefully have high precision measurements with an electron ion collider, and all going to be very happy and excited about this, right? But okay, that's only going to happen a few years down the road, right? And so for the moment, we have to live with what we can do with kind of present-day experiments, right? And so, okay, of course, one of the things to look at there is to look at hadronic collisions, PPA, right? That we can see it. And so one of the interesting processes where we can somehow probe small x dynamics, right, is to look at the forward production of dihadrons or dijets, right? And so basically the process I'll be looking at is, right, okay, so we have a proton colliding with a nucleus, right? We're going to look at the forward in the proton going direction, right? We're going to be producing two particles, and at the parton level we produce two partons, right, which can be detected either in terms of two hadrons or two jets, right? And so looking forward, we can select the kinematics essentially. We have a large x in the proton, right? And we pick up very small x, and hopefully with that somehow a sizable transverse momentum also from the nucleus. Okay, so of course this is nothing I came up with, right? I mean, this is a field that's been studied for quite a while, right? And so in the case of Rick, there are even some very exciting measurements, right? And so what are we looking for in general, right? So okay, so usually, say for the PCD, we produce two jets, right? They're going to be back-to-back at leading order, right? And so what we want to see is that, okay, if we now give it a large transverse momentum transfer from the target, essentially, right, then this can affect the back-to-back nature of the two jets, right? And can lead to an angular decorrelation of the two jets, right?
What do you mean by high PT?
Oh, it's high. How high is high PT?
Yeah.
How did I mention high PT? Ah, okay. So I mean, let's be. You referred to. Yeah, I didn't even say that. Okay, so I should be more careful when I write on my slides. Well, I mean, okay. So I mean, what do you want to do, right? I mean, the momentum we can get over here is on the order of QS, right? Okay. So this is. Right, so that's okay. So right, and then what QS is depends on kinematics and so forth, right? And then okay, we also have to live with what we can measure, right? So in the case of Rick, right, I mean what they measure is written over here, right? They measure hadrons above 2 GeV.
So high PT is just the whole PT of the hadron.
Yeah, exactly, right? So in this case, so in the case of Rick, what's been measured is hadrons of forward rapidities, few GeVs, right? So always dominated by the lower PT part, of course, right? But that's what you get. So in that sense, high PT is not actually that high, right? At least not to what we think about the central barrel somehow, right? But okay, it is what it is, right? Okay, so idea is, right, we get this kind of pick up this large intrinsic transverse momentum from the target, right? Because due to multiple scattering of fluids essentially, right? And so this can lead to the angular decorrelation of the diagram, right? And so if you look at if you look just at the data, so solid points here being PP,
Open symbols being D gold, so just you can think of as P gold, I guess, for this purpose here as well, right? Then, okay, indeed, comparing the data, right? Okay, well, you always have this, at least in hadrons, it's very clear, right? You have this kind of near-side fragmentation peak, right? So essentially, you just have a breakup into multiple hadrons, so you get an enhancement at the near side, right? But you see really this nice suppression and with some fantasy, maybe broadening also on the away side over here, right? And so qualitatively, you may say, okay, I'm very happy, right? I see what I'm after here. Right?
So what broadening? Where do you see broadening?
Well, with a little bit of fantasy, this is broader than the.
I see. So the empty circle.
So you want to compare the empty, yeah. So you want to compare the empty symbols to the full symbol.
I'm sure star collaboration is reasonable.
Is star collaboration here?
Okay, never mind.
Okay, never mind, right? Okay, so good. So I mean, okay, so on the qualitative level, at least, okay, this seems to be something worth hunting for, right? What is also shown here is actually some small x calculations by Cyril and company, right? And so okay, so I mean they also calculated the effect that you should be getting, right? So this is, I mean, I'm going to talk about how they, I mean, what some of the content of these calculations is later on, right? But okay, I mean, what you can actually see is that if you compare some of the width that you get from the theory calculation to the width that you observe in experiment, right? Then okay, I mean, this is really a whole lot narrower, right? Than what you see experimentally, and this basically has to do with the fact that okay, I mean, of course, we're not only seeing the effects that we actually want to see, right? But there's other effects related to, well, I mean, in this case, I think this is mainly like Sudakov effects that you see here, right? So related to kind of extra soft gluon emissions, which also compete with what we're actually hunting after, right? And so, okay, so this may be.
But Sudakov don't distinguish proton.
No, this is true, right? But I mean, the thing is, the width in proton is already way too narrow here to actually.
But if you
I mean, the broadening on top is, yeah. So I mean, you could try to look at it differently, right? So looking at
the change when proton has Sudakov broadening and no multiple scatter, no QS.
Exactly.
When you do proton gold or deuterium gold, the Sudakov is the same, and then the additional broadening.
Yeah, sure. Yeah.
Just minor question on this. So Sudakov logs are logs of Q squared over KT squared. If a typical KT is of the order of QS, then you would have logs of Q squared over QS squared, and those would be probably different than PP.
No. It's just, in PP, you have to look at the same transverse moment.
Well, but this is integrated, right, over PT. So if you look at an observable integrated over PT, this is not really integrated with PP. So this is really greater than 2 GV, which practically means PP equals 2 GV.
Yeah, and so I mean, so one guy is above 2 GV, and the other one is between 1 and 2. I mean, this was the first picture I found, right? I mean, this is.
In practice, it's fixed PP.
Yeah. I think your point is right. You have to get, you have to do a comparison. See, the Sudakov effects are the same in proton, and proton gold. So you have to
fixed PT. For fixed PT.
Yes, you have to compare the same things, of course, in the two. It's not going to be the same if you do different momenta in the two different processes. But if you choose the same momenta in the two processes, Sudakov is the same.
Yeah, but if you look at some integrated observable, and we can debate how integrated this is, and maybe not very, one would probably have
that's these things. Everything isn't a gift. The phenomenologist has to do something.
If you look at the data, the TP and the neutron gold are as wide, and they're both wide.
I have a question about that.
Yeah.
Is the interval under those curves supposed to be the same?
No.
If you have limiting fragmentation or something like that?
Well, it should be the same, right? I mean, you've got two jet event, and ideally it should. You're not.
No, it's not 2 jet.
You're not doing jets.
No, this is hadron. This is hadron. I mean, this is what you can do at ring. This is what you do at ring.
There could be induced radiation.
Yeah.
There could be induced
Yeah,
radiation.
and the fragmentation region of the proton.
In the second jet, the right-hand jet.
Yeah, but that's what I'm wondering. But the right-hand jet is a leading particle, right? Proton side.
Well, it's more than just the leading particle.
No, this is the, I mean, this is the back-to-back, right? So this is, I mean, this is the fragmentation of the single jet, right? And this is the back-to-back jet, right? As you see here.
Oh, I'm sorry.
Right.
I'm sorry. I
Right.
misunderstood.
And so this is fragmentation of the single guy. This is the
So
back-to-back
this is
jet.
the what rapidity then? I thought you
So this is
said
between
forward.
2.4 and 4. Right?
So if you really went at the forward region, the interval should probably be the same. But if you're away from in the central region or the other side,
Well, I think that
Why should the
there's
integral be
always
the
the
same?
issue if you're measuring particles, there's always the problem that if you're measuring jets, and azimuthal angle, then when you integrate over it, you should find one. Except the fact you could push some events outside
Right,
the jet cone, right?
Yeah.
That would change it somewhat. But if you're measuring particles, you do have to worry about induced radiation. And if you count these numbers of particles, there's not a conservation.
yeah, for central and stuff like that. But it,
Well,
forward,
even forward.
I mean,
well,
the
far
RPE
forward, I would. I mean, you don't expect it's going to be.
I remember
See,
the-
he's expecting multiple scattering, is what he's looking for.
Okay, so
If there's multiple scattering, it
so
also
they-
induce
so
some
there'll be
radiation.
small
Yeah.
multiple scattering effects which you want.
Well, it's not supposed to be so small. Ideally, we would hope to get a typical transverse momentum broadening of about 2 GeV up here.
Look at the data. They're much wider in proton in the calculation of the column last time. It's not only five.
Yeah. And so I mean, so I should say this, right? I mean, so I think there was some calculations recently by Anna Stasto and collaborators who tried to include Sudakov resummations also and so forth, and they do a much better job on this, right? But okay. Anyway, so this is okay. Okay, so
Without any Sudakov.
okay, good. So then it's even more interesting, right? So then it's good. Okay, so we this is good. Actually, I'm gonna go there, right? Because okay, so let's. I mean, we can continue discussing this, but I just wanted to say a couple of words on what you can actually do with experiments. Right. So in Rig, as you say, I mean, so apparently all we can do, or at least all I've seen, is to do dihedrons, right? But we also actually have fantastic capabilities at LHC, and so this is kind of how I got hooked up with the Kansas guys. Because the thing is, actually at LHC they have a fantastic coverage also in the forward region over here. And so they have, I mean, for instance, this Castor calorimeter, right? So this is something that Christoph is involved with, which goes here out to rapidities of something like 7 almost, right? And so you can go to really, I mean, you can actually go to really, I mean, probably really small X also in the nuclear sites there, and you can actually in this forward calorimeters, right? You can not only, I mean, you can not do hadrons, you can actually do reconstructed jets, and you can do them to PTs of something like 3 GeV or so, right? So the thing is, these are highly energetic jets, right? I mean, but because they're flying so far forward, right? They can do them actually to something down like 3 GeV or so.
Reconstruct jets.
They have it. So if you go and look at this thing, right? They have reconstructed jets at 3 GeV down there. And so Christoph optimistically tells me they can even do maybe 1 GeV.
Oh,
but they haven't done this yet.
They're not jet.
No, but it's very high energy.
Yeah, these are 500 GeV jets, some of them, right?
500 G, yeah, it's 100
But the PT,
They're very forward.
right?
Yes. See, no, that's very interesting because in central regions they can't even construct 50 GeV jets.
Exactly. Yeah. So this is why it's very interesting, right? So first of all, they have a more or less continuous coverage, right?
So
Yeah. Well, it's the garbage that goes along. So no. In the central region, the problem is the garbage. At LHC, there's so much junk going along to separate a jet from all the garbage. If they can do it at 100 GeV, they certainly can't do it at 30, 40, 50 GeV. Right.
Yeah.
And so you said there's no garbage going forward here.
Well, that's. I mean, I'm not the. I mean, I maybe not the. Look, I tell you. I mean,
this
I
is
look
not
what
just
the
a-
experimentalists
this is
say
not
they can
just
do,
an
and this is what they say
It's
they
not
can do.
just an issue of what they can measure,
yeah.
it's what the garbage underneath the event is, what the fluctuations are.
So by garbage, you mean just whatever, producing soft pion or
Background
something
events,
like
you know,
this.
the background events they're
Yeah.
tremendously high in LHC.
Yeah. No, I mean, so I remember one should look more closely at what they have done so far, right? So then they look at this and they say, okay, look, this really looks like a jet. This is a jet.
Which is barreling down. So you have people at the 3 GeV tensors. Have lethal at such a small number?
I don't know.
They find the jet to be
So this is the main particle. They measured them.
This is the momentum of the reconstructed
Of the whole jet.
of the whole jet.
The whole jet carries 3
The
GeV.
detector is very far forward.
Yeah.
The detector is very, very far forward. So you're looking at something that's gone a long, long, long distance. Right?
So you need to know the angle.
Yeah.
And then.
And they get to measure the, I guess, the
But it's not a written particle, it's the whole jet which has 3 GeV.
No. The particles from the jet.
No. This is I think this is the whole jet. This is the whole jet.
All get all the particles from the jet. All the particles together. No, sorry, individually. Sorry. The highest part, the highest.
No, it's the jet.
They don't have particle identification concept there, right? The whole jet.
Exactly.
Yeah, because that's an easier measurement.
Then they don't really particles. They're all on the jet axis. If together have 3 GeV.
Yeah, but okay.
It's very interesting.
So it is what it is, right? But I mean, so the point is, right? So this is really, I mean, they are dead. So for instance, in Castro, I don't think they have. I mean, they don't have a dijet measurement out there, but they're working on this, right? And so, I mean, the point I want to make is, that, I mean, this is actually fantastic for the kind of physics that we want to look at, right? Because first of all, I mean, we can go very far forward, right? We can apparently measure jets, right? But not only can we go far forward, right? Because they also have a sort of continuous coverage here, right? And so you can do all kinds of crazy things, right? You can do like one jet in Castro, and then you can start looking for the other jet somewhere else or something like this. So this is really, so I think this is not being fully explored yet, but I think there's a wealth of interesting opportunities to look at, right? Okay, good. So this is the motivation. So now let's go to what I actually wanted to talk about. Okay, so So idea here is to talk about our dijet production in the frameworks that we use and love, right? And so I'm going to address this kind of in 3 parts, right? So historically I started from the bottom, but that didn't get very far. That worked the way backwards to the easier things, right? So okay, so I'm first going to talk about dijet production in just dilute-dense, and then the way that this is typically implemented into phenomenology, reducing sort of the full CGC calculation to a framework of TMD factorization, and so they'll somehow give results for small x TMDs at finite NC in the mean one. I'll then also present some kind of more numeric studies of actually calculating the dijet cross section in CGC GymWalk framework. And then finally, this is maybe the most interesting part, if you want so, which will address dijet production at unequal rapidity. So where you really have a large rapidity separation between the 2 dijets, right? And you have essentially evolution between the 2 dijets as well. Okay, and so here, so this is the disclaimer, right? So everything I'm going to talk about is preliminary, right? So, but hopefully all this will be interesting. Okay, so so how does dijet production work in dilute-dense CGC, right? And so, okay, so what do you have to consider? Well, okay, so let's look at sort of the standard diagrams here. Okay, basically you pick out a parton from your projectile, right? And okay, so this parton will have to split essentially into 2, right? Which are going to be your 2 measured dijets, right? And so this can happen either before or after the interaction with the shock wave, right? Okay, good. Then you go and calculate the cross section. This is what Cyril did more than 10 years ago, right? And so okay, cross section looks what it looks like, right? Okay, so this usual stuff up front here, right? And then you basically have all the matrix elements of the color fields, right? Which correspond to the different possibilities that this can happen in the amplitude and in the complex conjugate amplitude. So you can either have scattering of a quark, scattering of a quark-gluon projectile, or scattering of quark-gluon projectile, and then all the different combinations in the amplitude and complex conjugate amplitude. Right? So probably the difficult part about this is that, of course, if you have the quark-gluon projectile both in the amplitude and the conjugate amplitude, right, you essentially pick up a rather high correlation function of the fields in the target, right? So which is I think in this case would be something like a 6 Wilson line correlator, right? And so it turns out that even though this was calculated 10 years ago, nobody has actually used this to actually ever calculate a dijet cross section.
Well, we don't exactly evaluate the two.
The
It's not
Gaussian
exactly
approximation.
that, yeah.
So what you do is this. Do you need this?
Yeah. Yes.
Yes. Okay. See, you're on the next one.
Okay.
Okay, so what do people do, right? And so, okay, so I mean, so to actually go and do phenomenology with this, this is usually done based on different approximations. Probably the most, indeed, what I would say the most elaborate thing that was done today was probably what you guys did, right? Where essentially people approximate these correlation functions of the field, and I think this is some kind of, so I looked at the paper. The way I understood this was a mixture of a Gaussian large NC approximation, where basically this sort of complicated Six-Wilson correlator is then factorized into some simpler object.
What like I found not that term.
Yeah, so it's not a large NC, but it is a mean field approximation, a mean field approximation.
Okay, good. Yeah. I mean, it's not a very large NC is also mentioned in this paragraph. So I think in large NC you can also factorize this, but you would also drop this term.
So the point is that you can, I mean, the S4 is a dipole times quadrupole. Then the approximation we do is that we replace the expectation value of dipole times quadrupole times by expectation value of dipole times expectation value of quadrupole. So it's a mean field approximation. Yes. But then after that, we evaluate them at finite NC.
Yeah, okay.
In the Gaussian.
We have both large
We
NC
have both.
and finite NC for quadrupole. So.
So
Good, okay, so
it's also a finite NC, but it does have a mean field approximation to reduce the 6-point function into a 2-point function times a 4-point function.
Okay, so I mean, so in essence, the thing is, okay, so you can do two things here, right? You can either try to do simplifications on somehow what is the structure of the color fields, or whether correlation functions of the color fields of the target, right? Or you can try to, this is sort of the other approach, try to work in certain kinematic limits, right? And where automatically simplifications occur, right? And so that is that in recent years has been used very widely for phenomenology, because this simply makes the whole calculation a whole lot simpler, actually, right? And so, okay, so when I entered this business, I kind of like look what people do, right? And so I mean, so my natural question was like, okay, so like,
But the simplest one.
right? Like, not what is the simplest one, but like, okay, so I mean, how good are these, right? And like, I mean, okay, so can we actually do the full calculation and somehow, see what is, what turns actually out to be?
Which one has any evolution? I mean, seems like point
No, so
is just the mean model.
No, it's a Gaussian with evolution. It's a Gaussian approximation.
Yeah.
So this is BK evolved dipole.
We can express.
So you use a Gaussian approximation.
You use a Gaussian
So
approximation.
you need quadrupole to dipole. And
Yeah.
dipole is one of the
That's what I would do.
Yeah.
So just, okay.
Yeah.
Yes.
Yeah, so that's what's been.
It's probably not right.
It's very wide.
So far, nobody has really seen like a clear indication of where it would not be.
Exactly, it's very wide.
There's no clear
All the calculation
indication
of the quadrupole from GMO gives the same type of Gaussian approximation.
So this, yeah, so I would say the same. So this presumably is pretty good, right? But I mean, one should still check, right? That's the point. But what is okay? So let me move on here.
No, it's surprising, but I think that it was so numerically by Lapin, by Thomas, we had an analytical proof with Edmond that if you have an operator that it has a non-trivial dilute limit in the sense that it starts with a two-gluon exchange approximation, then you can approximate quadrupole blah 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 in terms of dipoles. Of course, it's a complicated formula, but you can do this. And then, I mean, you have perfect agreement in the dilute region. It is exact at saturation, because at saturation you have only Gaussian should be okay. In the dilute limit, you have only one correlator which determines everything. And around QS, we had plots where the error is like 2%. But whatever correlator you choose, of course. I mean, of course, you do choose some kinematical limits, but it works. If you take now, let's say, more complicated correlator, which in the dilute region, it may have like an Oteron type, or starts, let's say, the two-gluon exchange limit is cancelling, and it starts like with 3-gluon exchange or 4-gluon exchange, then it doesn't work, because you have more correlators in the dilute limit that you cannot capture from a Gaussian, which has only one correlator. So somehow it works. I don't know. And then it's not
But
surprising.
the proof is only deep inside the saturation region.
No,
or
also
deep
in the
or
dilute.
outside.
Oh,
But
not
not
the
not in the middle.
Yeah, but
Yeah,
the middle is very constrained.
In that case, yes, but look, I mean, you have so many errors in that thing that if you are bothered by 1% or 2% in that thing, then
I'm not
okay,
bothered.
I'll just give up. It's not exact.
Okay, so it sounds like approximation A is very good.
It's a good approximation.
What do you
but
mean?
Well, it
It's not
probably is.
exact, yes.
I would still like to, but I mean, look, right? I mean, if we have this formula for the cross section, we should at least try to calculate it, right?
I would be very happy to say it out from this one.
Good.
With Jim or
If I'll get there, you will. Right? Okay.
So Cyril is missing, but what does he get? He does this code.
So what's it?
Not a high PP, but he looks at small one. In that case, well, in that case, you should have a bicycle Williams, right? It's not a quad.
You know, there's this code with Clodo and which solves GMO for each line, and then they can build the operators and give
Yeah, they do the operators, but then they go to this correlation.
Yeah, so-
because they want to write it in terms of
2-point
this.
function.
They want to write it in terms of they want to extract the 2-point function.
They don't
So they do the full thing. So they do the full
It's too
thing.
complicated for
But then instead of using the
convolution with
full
4-point
thing,
function.
yeah.
Okay, so I mean, actually, okay, so I mean, so this, even if you do the simplification, this is still a very complicated calculation. Actually, I would say so. Actually, what's much easier to somehow use for phenomenology is essentially the second one, where you go to what is called, or what people call the correlation limit, where basically, okay, what does one look at? So one has the two momenta of the two, so one has the momenta of the two dijets, right? And one basically goes to the limit where the momenta of the two dijets are both much larger than the momentum imbalance of the dijet pair, right? Which can be on the order of the saturation scale, right? And so basically, if you do this, what happens is that essentially, okay, I mean, the kinematics is forced such that this kind of complicated 60-section pole operator becomes simplified. You can expand it around certain coordinates, and that actually then leads to a very, very simple form of this horrible cross section, which is equivalent to the expression you get from TMD factorization. So in that case, the cross section becomes very simple, right? And you can see no longer any integrals, anything, right? So just a couple of kinematic factors, some hard factors, and essentially all the information about the fields of the target is then encapsulated in these various small x TMDs. And so following the calculation in what is called this correlation limit, it essentially reduces to the evaluation of the set of these small x TMDs then, which, okay, so you can now try to evaluate using various different formulas. Now, the thing is this, okay, so usually what people...
Can I ask you, because
Yes.
I have not followed the details of that, but this is still includes some non-linearities, that formula on top, because delta application...
Yeah, so actually, if you look at, for instance, what these TMDs look like, right? So you'll see, okay, so for instance, you have this TMD F6GG, right? This probably 6 operator they found, right? You see, okay, this still has a rather complicated structure in terms of...
Momenta are hard, but the problem is not.
Yeah. So basically, what happens is, right, so that instead of having your 6 Wilson lines here, all the different coordinates, right, just some of the coordinates that eventually coincide, right, because that's what you enforce by the kinematics. And so that's what then makes this a whole lot simpler. Okay, so typically what so this is very nice to work with in phenomenology, right? Because again, you need to know the subvectors, and it's just some simple whatever SU over T or something like this, right? And the only input that you need from small x physics is essentially what are these small x TMDs, and then you can go ahead and then very quickly calculate a lot of stuff. Right? So I mean the only challenge is then, okay, how to evaluate these TMDs, and so typically what people have done so far, they have done this in this Gaussian approximation at large NC. So the operators that you're facing with are, okay, so in the case of where we produce the digest starting from a quark, so quark plus a gluon projectile, you have 2, right? So one is kind of the usual dipole, right? And it's something where essentially the gluon also scatters from, right? So which already involves 1, 2, 3, 4, 6 Wilson lines, right? And so in the case of the gluon, you have somewhere you should have the Weizsäcker-Williams. Here this is the Weizsäcker-Williams distribution, but you also have these kind of more complicated correlators over here.
So if you assume some sort of a center of mass integration, it's automatic, that's a S-curve factor.
Yeah, that's assumed here. Yeah.
So
impact parameter depends in all of these studies is treated extremely, how do you say this? Yeah.
Cavalier.
Extremely cavalier. Yeah? And that's actually one of the reasons I would say it would also be interesting to go back to the original calculation, where in principle you have this beta in there.
Why do you distinguish F3 and F4? It looks like one
Because they do.
just information contribution.
Yeah, this is exactly the same. Yes.
Okay, so F4 is F3 of minus k.
Exactly. Yeah.
So why do you not call it F3 of minus k?
Because they call it F3 and F4, so I just call it that.
I mean, so the notation in usual TMD world is if something is a function of absolute value of kt, then it's derived as a function of kt squared. Now, right?
Yes, you could do that here.
So are these all functions of kt squared?
Yes.
And then, yeah,
No.
then, no?
Not the way that you're some of them, okay.
No, but I mean, once you exploit rotational symmetry, of course they are. Right?
Yeah.
Their own rotation is symmetric,
Yeah,
right? So then really it's not.
Yeah.
So how selects only the k square part of those.
Right.
But
So,
for more involved processes, these TMDs could have other accounts.
are you saying
The
it's
way
not
that
real?
they
It may be a function of kt
Some of
squared,
them
but
are
it's
not.
real.
I'm not sure about those written here, but in Zurich's paper, there are some which are.
I mean, this is in principle.
Anyway.
I think this is in principle exactly the same as in Cyril's paper. Okay, good. So new thing we brought to the table here is that so actually when we calculated these guys in finite NC, right? So I mean, of course, some of them are known. 4 Wilson line correlator, 2 and 4 Wilson line correlators are known, but turns out you can actually, for the thing is, right, I mean, you have complicated operators here like octupoles and so forth. So this one over here, this one over here are complicated, this one is complicated, right? But the point is you still only have 2 distinct coordinates, so you can actually still go ahead and actually evaluate them in Gaussian approximation at large NC. And so, I mean, actually, result you get is not even at large NC, at finite NC, right? The result you get is not even that complicated, right? So fits. So these are the 3 ones which are in principle non-trivial. This is the 6-point operators. These are the 8-point operators. But I mean, so they still kind of fit on a single slide. And so this is what I mentioned to Daniel earlier. So this in principle corresponds to some of these guys which have these extra box insertions also, right? So this is something that we can actually easily calculate at small x.
So you can fit anything on one slide if you use Font's model.
Yeah, I mean, this is a screenshot scale, right? But it's really not. See, the thing is, you can actually automate this entire calculation, right? So this is actually how I did, right? So you can automate this entire calculation in Mathematica. Most complicated step becomes actually transferring the result to a LaTeX formula. Yeah? Okay, good. So, so what we have here? Right? And so, so kind of interesting to ask then maybe how important are actually these finite NC corrections compared to the large NC where you get much more complex formulas. Yeah? And so so why is this useful, first of all, to have at all, right? So basically the way these guys are expressed is, right, so you look at whatever any TMD here, right, so it's 6, right, and so they only depend on essentially the logarithm of the dipole amplitude, which kind of gives you adding single gluon exchanges to the ladder, right, and so they only depend on this and a bunch of its derivatives and a bunch of color factors, right, and so the reason that this is useful is that in principle the dipole amplitude is something you can obtain from RCBK evolution or so, right? And then you can, once you have your dipole, right, you can directly evaluate what all these TMDs are and use them in phenomenology. So, how important are these corrections? And so,
Sorry, I got confused. So
yep.
What you just said, how is this different from IT?
So he's using this is without the mean field approximation. If he was using a mean field approximation, so he wrote a finite NC. He was using a form where a finite NC you have a dipole times quadrupole, expectation value dipole times quadrupole, and he was approximating this by the expectation value of dipole times expectation value of quadrupole. So he was factorizing the 6-point function into the product of the 2-point function and the 4-point function, and evaluating the 2-point function and the 4-point function in the Gaussian approximation. What he's doing is that he's evaluating the 6-point function, the full 6-point function in the Gaussian approximation. field.
But in the TMD limit, right? I'm doing it.
But again, on the other hand, in a certain.
On the other hand, in the TMD limit.
When I say
I'm not sure I understand, right? So
So KT
you
was
take
working
and
with
you-
4-point functions.
well,
Yeah.
actually just do the expression as it is, right? By written by zero.
Yeah.
Just evaluated it using Gaussian. And
and factorizing the product.
The traces.
Yeah, so the
but
expression.
the fact that you
so-
do it anyway, right? When you write
So you have something
it,
like this, right? You have like a 6 point.
This is Simon's expression. It's a 6-point function.
Right, you have a 6-point function. What you guys do is you say this is 2 point times
Because it's a
So in terms of
it's an
six
adjoint.
fundamental.
6
It's fundamental.
fundamentals.
It's fundamental.
Okay, and you can replace that's a latch and C
No, this is
and a latch nucleus term.
this is what Thomas calls
No,
right?
no. If it's a simple trace on the left hand
Cannot
side,
be summarized.
It's not correct.
No,
It's
so
not
not
right.
right. Okay, he's not right. He's not right. He's not right.
if it's trace of the trace of one, yes, it's like a 3 plus, like nucleus
The operator is
Okay, so if you fuse it together, that's what you're saying.
the operator you want is this. This is the full. It's a 6-point function.
Yes, okay.
Trace of 2 times trace of 4.
Yes.
Okay. The approximation Heikki was using was to.
Yes, so
So
that's
the-
latch and C and the latch nucleus.
Yes.
But then
Okay.
what Heikki was doing was taking both this and this at finite density.
Right.
So it's
using Gaussian again.
Yeah, using Gaussian.
MV.
Yeah.
And so,
Yeah,
suppose-
so what he's doing is that he's not doing
so
this
he's
approximation.
doing it in opposite order. He first uses MV.
So what he's doing is that he's evaluating this full thing, the 6-point function in the Gaussian, but in a certain coordinate limit where instead of 4 coordinates, he only has 2 independent coordinates.
Right. I understand the TMD implications, but so he's doing it, and then each e to the g he replaces by the S matrix of RCBK.
Yeah, so
Right.
it's
So
just,
essentially, it seems like it's just doing the same thing in a different order.
No,
well, it's there. It's
very
using different
different. You're working with
approximations.
2-point function or 4-point function, right? When we went to 4-point function,
Well, in the end, seems like everyone's working with 2-point functions.
No,
In the end, yes. But in the end, yes. But it's a different different approximation of how to relate how to write the 6-point
Is it
6-point
really
function in
different? Is it
there
really
a way to relate
It is.
So in the end of the day, whether
So
you, sorry, can I ask my question again? So suppose you do it one like the other.
Yeah.
In the end of the day, you get an expression similar. Can you show the other slide that what you didn't like?
this
Yes.
one.
The one. So you get some expression in terms of G.
Yes. Yeah.
And Heikki got one.
So Heikki's expression would not be the same. So if you take Heikki's expression of what he was using and take the same kinematic limit, the coordinate
Right.
limit, so that you can compare. Heikki's expression does not reduce to precisely this.
And the large NC,
in the large NC it does. Yeah. So there are 1 over NC squared, 1 over NC correction or 1 over NC squared corrections that are correct here but missing in what they used to.
And who is more precise?
Yes, that's right.
Well, there's two approximations.
Yeah, so at the present point, there's 2 approximations.
These are sort of two approximations. So for the full expression, there's 2 different approximations you can make. So there's two different approximations. Søren is doing one of the 2. Heikki is doing the other one of the 2.
But usually when
Which one is more precise depends on how it depends on.
nicer.
Somehow there are so what,
like on the kinematics,
Yeah,
how
yeah.
good is this?
so it's a question. It's a question. So but Søren
The approximation is valid in the
Okay. So Søren is taking this correlation limit. So Søren is assuming that some ratio of 2 different transverse momentum scales is small. Okay. And Heikki is doing a certain kind of a large NC approximation. So the question is this coordinate, is this momentum ratio that Søren is assuming that is small, is this momentum ratio big or large compared to 1 over NC squared? That determines which approximation.
But in principle, this is exactly, I mean, so the reason I'm doing all this stuff is to exactly answer questions like this, right? And it is like, okay, right, to actually go and evaluate these B's, I have to make approximation A, B, C, D, right? Yeah. And so the only way to find out which one is better, right, is to take the full thing, evaluate it, and compare different approximations.
Where are you going to imagine applying this? Is this going to apply at CERN? No.
Yes.
Okay. Then that K-perp over Q-perp is minuscule, right? The Q-perp, if you apply to CERN data now, is 100 GeV.
No, but
you want to go this very forward regions, right?
Okay, very good.
Yeah. So you have to be careful, right? I mean, if it's you can.
So you're thinking of the not the analysis that have been done so far, but the ones.
The ones that are coming up,
but
right?
if it's not small, then of course the validity of this thing.
Yes, absolutely.
Yes.
So yes, you have other error bars, but
Yes.
just the two procedures of evaluating correlators. I don't know, Dionysius, you have this analytical statement for them. Which one?
So at the level of the, so look at the level. So here's something. Let me bring one up.
So yes, Dionysius' statement was not. Dionysius' statement was about a different thing. So what Egi is doing is a further approximation beyond the Gaussian approximation that Dionysius was referring to.
Look, sorry. If your starting correlator satisfies Dionysius' condition that it reduces to the dilute limit, then you can just do that approximation right away without making any steps, and it should work. Or you can.
You ask me and then you discuss with him. I don't understand this. But don't refer to me, okay?
So
you
can, but the physics point is a complicated. But
They're trying to explain what
you
you
can. So you can, but the physics point function is a complicated thing.
No, I cannot explain it more because
he was using one approximation. Too late. CERN is using another approximation. Nobody has really, I think nobody has really evaluated the full 6-point function in the Gaussian.
No, I disagree with that. No, so he just erased that. So basically, you can use the Gaussian approximation to evaluate with 1 over S square corrections the trace of 2 times the trace of 4.
Yes,
okay? So you can do that. So in that sense, what Soren is doing, to me, modulo the Gaussian approximation and that kinematical limit that he has the full thing.
Yes.
Yeah.
Yeah. So
if you factorize, 2 Wilson lines times 4 already, but then you keep some 1 over NC or other stuff. So to me, what Soren is doing, modulo the kinematics, which he has to do because it's difficult for me, it's okay.
Okay, so because that's
yes, so then for me, it is perfect what he's doing.
It's because it's simple, it's calculated.
I don't see any loop
because convolutions are simple.
Because there's, the beauty.
But the point is, well, you write the expression for the full 6-point function, but it's an expression that nobody has really evaluated in the full kinematics. So the reason Zorin is able to do it is because he's taking
I'm taking a TMD.
He's taking a TMD limit where it's simple.
Yes.
So the expression that you say can be evaluated through it
can actually not be evaluated.
but it's nobody really has because it's just a complicated
Sorry,
calculation.
so
Possible but complicated.
Sorry, just to understand you. If you were to start with serious expression,
yes,
fine. But I was saying in practice nobody has
the
evaluated.
problem here is all those
What you
multiple
say
Fourier
in principle it's
transforms. That's what you're really afraid of.
So there's a couple of things here which are complicated. One is doing eventually all the integrals and stuff like this over one, and the other one says, so that's from a numerical point of view. If I wanted to do as much progress as possible analytically, then I'm already stuck here with evaluating this very complicated correlation.
The difference is because the coordinates are different.
Whereas in the TMD limit, the coordinates coincide, and then you can actually calculate. I mean, if you only have 2 coordinates, I'm confident you can calculate probably also.
I see.
More than octave.
So the plausible thing to do is to take all these correlators, do the Gaussian approximation as Dionysius says, and then do the dipole, kind of replace e to the g to the minus g by the dipole as matrix.
But then you have how many integrations to do there, right?
No. I'm not saying it's a walk in the park. I'm just trying to say that this is still kind of
possible, straightforward, but very tedious.
So here's look, guys. Let me make a remark here. Okay. So I'm going to compare 3 different things throughout the course of this talk, if I ever get it. I will actually show a full evaluation of this thing, right? Yes. I just haven't compared this to anything yet because it's very complicated. Okay. Now before I do that, I do what is actually useful for phenomenology because it's very easy to calculate a lot of stuff. I take this TMD limit, right, where I don't have to do any integrals or anything. I just multiply 5 numbers and I get a result for the cross section. That's why this is beautiful. This is very practical to use. Now, this is only valid in a certain kinematic region, but it's super easy to do phenomenology with it once I know what these small x TMDs are. Now, the small x TMDs, right, I can calculate. I'm calculating them in this Gaussian approximation, right? But I'm keeping finite NC terms. And I can, okay, in doing so, since this is the first time this was done with finite NC, I should also look at how important are these finite NC corrections actually. Right? So this is the one thing I can actually assess within this TMD framework at least. Yeah? Okay, so this is basically the summary of this result, right? So what did I do? So I calculated them. So I took the MV model, okay, and so the MV model is Gaussian by definition, right? So somehow my Gaussian expressions for the various TMDs should be exact, right? And so indeed, so the full lines here correspond to the Gaussian expressions for the various TMDs, right? And so I've compared this with a numerical lattice calculation of the same TMDs, and you can see, okay, these guys go to every single point.
So the numerics is also in the MV.
The numerics is also in the MV model. So I put the MV model on the lattice ones, right? And in the other case, I use these guys over here in the simpler ones. Yes, I want to know whether these formulas are right. Right? This is a cross-check in the sense that the two agree, but it's a non-trivial cross-check because, I mean, also as you may imagine, putting an operator like this on the lattice is not exactly a piece of cake. I mean, this was done before by Elena, right? But for instance, but okay, right? Nice cross-check of the calculations, right? Then on top of that, right, you can look at so the dashed lines here are actually so they are the large NC result of the same formulae, right? And so take these things, take the large NC limit, right? And so I mean, so of course, you know, I mean, so once you go above QS or something like this, I mean, they essentially all agree, right? But so you see, I mean, so it's actually kind of interesting, yeah? Because for quite a few of them, they seem to shoot this here at least. Okay, I mean, this is a logarithmic scale, so this is significantly below QS.
I played with that analytic some time ago. We never wrote anything. I think I know why it was happening. Now you work in momentum space, but if you work in coordinate space,
yeah.
The problem of the large NC limit sometimes was depending on the correlator you may want to calculate.
Mm-hmm.
If your correlator contains some singlet part, okay,
mm-hmm.
if you start playing with, then it doesn't go to zero when you are deep in the infrared. So usually you expect all your correlators to go to zero because they're trace of Wilson lines
mm-hmm.
or like S-matrices.
Yeah.
But some of them, depending on the combinations
mm-hmm.
that you have there, they may contain a singlet part. Okay, and then this is not going to zero. Okay,
exactly.
And in that case, if you take the large NC limit, you are losing that part, and your correlator goes to zero. So I think now you take the Fourier transform, so it's not similar, but I think this is what this is.
This is potentially. I mean, so to me,
but it doesn't. But you see, it doesn't happen in the dilute regime, right?
Yeah, no, the dilute regime, everything is fine, right? But if you,
so I think that's the issue.
So if you go below QS, I mean, you do see that there's somehow.
In the large NC limit, the adjoint dipole doesn't go to zero.
Exactly. That's an example. That's an example.
Exactly.
This is an example. Exactly.
Yeah.
Numerical lattice means what?
It means, you know, doing the usual thing. So you create an ensemble of Wilson lines, right, by rolling the dice, right, and then just measuring exactly that correlator on the Gaussian. So yeah, with the Gaussian, like we always do, right? So I mean, that's why the two calculations have to be equal, actually, right? So it's just a good check. Yeah.
Why do you show this QS squared line?
Because this is I think the asymptotics in high PT. Okay. So at high PT they all go to the same asymptotics essentially. Yeah. So that you can see.
So the numerical lattice just checks you didn't make this.
So the numerical lattice, exactly. So the numerical lattice is just a further cross check of this finite NC Gaussian result essentially. Yeah. So you do see. I mean, okay. So you do see this. I mean, quite a difference here somehow. Momenta is smaller than QS, and it seems to me somehow like there's some kind of logarithmic enhancement here in some of these things, which simply the large NC seems to miss, right?
If it was a constant, then you take the Fourier transform,
Yeah.
Depending on
Yeah.
the reason, right?
Yeah.
It's like the T matrix theta at saturation is 1, but if you calculate the fluid distribution, it grows like a log.
Yeah.
So I think it is the same thing.
Yeah, so I mean, it would be, okay, so I mean, one could probably go back and look at this expression and see where exactly this comes from. Okay, but okay, so then you can, okay, so this is, I mean, this is somehow, if you want to at the level of theory, now you can see if this actually makes any implication for when you now put this into the cross-section calculation. Now, I should say this is very, very preliminary what we did here, right? So this is now using factorization, this TMD factorization formula in the kinematics of this LHC Castor experiments. And so basically what I used here is I didn't do RCPK or anything, I just used the geometric scaling ansatz to evaluate the saturation scale essentially. And they just use this one parameterization of the TMD to calculate the cross-section. And so this shows example cross-sections here for dijets and dilute, 2 different PTs here, as a function of the azimuthal angle. So in principle, we're supposed to work in this decorrelation limit. So you should really only look at the case where they're very close to back. But okay, so I mean, what you see is overall the difference between these somehow large NC to finite NC result seems to be relatively modest here. Yeah? So this is probably not an important effect, right? But still, okay. I mean, it's still nice to do it. Yeah, probably do it. Huh? Thanks. Yeah. Okay, good. So this is okay. So this is the closest we somehow have gotten to actual phenomenology, right? Okay, but okay. So now that we have all the TMDs and stuff ready, you know, I mean, okay, so we'll start to continue to calculate there.
So what exactly is plotted on? What's the y-axis?
So it's yeah, this is cross section as a so the sigma divide in arbitrary units as a function.
You divided by proton something like that.
No, we didn't even divide. No. I mean, this Federico he did this last week. Yeah, so this is.
But you have the forward region DMDYD2PT, the single particles.
Yeah.
For single particle, yeah, but I mean these are 2 jets, right? These are 2 jets.
Yeah. So then you can calculate the average shift and average change in PT, like we're talking about.
And you want to now look at baryon, but this is a completely different calculation. Right? This is 2 jets.
Right? I don't care about variance. I would just call
These are jets and not particles.
Yeah.
Well,
I mean,
it's
You wouldn't actually calculate it from this. You would calculate from the single part.
Yeah, exactly. So this is doubling.
It's calculated the single particle.
Yeah.
So then you can answer this question: what's the shift in average PT and the shift in rapidity in the forward region?
Yeah, sure.
Okay. Right.
Yeah.
Sorry, what is this?
Yeah, but then you have to go beyond the important.
Why beyond leading?
Because recoil is important.
The condition.
Well, he had no
also
recoil.
there's a
Has no
type
recoil.
Which condition?
for
But
the
he's
on
done,
rapidity.
he's done,
It's anchor now.
On rapidity.
so yes.
Oh, yes.
he has a very-
Yeah.
so he has
It's-
a very- in the forward region.
That was the first slide I did, actually, right?
No, it's a
I think that was the
serious
first
issue.
slide I did. So that's the most time. Yeah, no, it's between 5.2 and 6.6. So this is what Christoph says. This is when it can measure. And so 3G above 3 GB, above 5 GB, some of the cuts they'll be able to do that.
So
Okay.
Evan says you haven't got the kinematics quite right for the launch because you haven't built energy and momentum conservation.
We're not interested in that. We're looking at the correlation.
For as view the correlations,
Yeah.
I believe you can do that, but probably with a single particle, DMDYD2PT will be messed up.
Well, I mean, I think it would be amusing. Look, since this is so revolutionary, I say no one at CERN has ever
agree.
looked at it. Right. The first thing I would like to see before you get into these very sophisticated things, you get the right answer for the jet cross section.
Yeah, I mean, I didn't care. Yeah. No. I mean, it's.
I wouldn't believe these numbers. I wouldn't believe anyone who tells me they're measuring 3 GeV jets. Look, lower energy accelerators never measured 3 GeV jets. No one ever measured 3 GeV
It's a
jets.
slightly different problem. I would like to know just globally how much of a PT enhancement you get
For particles.
per particle.
Yeah,
The
that's
total
what-
PT per particle. And also what the downshift and rapidity is of particles in the forward region. Those are important things for understanding things like heavy ions and to understand things which they can measure also correctly. And it seems can't do that yet.
So let's discuss about that.
So why were you so specific about 3G?
Look, even Heron never measured
No, I
3G
understand
jets.
that, but
Too low.
PT here is the momentum imbalance. It's not.
No. PT is the transverse momentum of the jet.
It's a
Each
3G
jet.
EV jet. And
I
now,
thought it was
and
this
now
momentum.
we're
I mean, the energy of the
correlation
jet
limit.
is
The delta
200
PT over
GeV.
PT should be small. So I guess the delta PT is 500 MeV.
I thought PT was delta PT.
No.
No. I mean, so delta PT can be very small, right? This depends on the
Yeah,
angle,
that's
right? It's PT1 plus PT2 and cosine.
So that's a
right?
calculation which is theoretically founded for hardware, not for jets. It is speaking for partners.
Well, I mean, you calculate it for points.
Well,
Yeah, you're getting a platonic level, right?
You know,
Yeah, what you do out of it is your thing,
that's why
right?
that's why I'd like to know this. First thing, just to see whether the jet cross section works here, right? If the jet, see, when you do high energy jets, you have predictions for the jet cross section. They work marvelous. So you have some confidence that you're really measuring jets.
So I have calculated forward jet spectrum in PA. You're using RCPK for Castor. It's not out yet, but I mean, it works pretty well in this framework.
At 3 GeV.
Well, it's a function of jet energy, but yeah, that's the PP ballpark, I guess. I think so.
And this is sort of roughly independent of cone size.
Well, it's a partonic cross section.
Well, I part cross section, so I just don't be part of
the data isn't partonic. So you go to you have a prediction. I read it. The prediction doesn't depend on the cone size, and you go down to 3 GeV. Now, when Castor takes their data, before they do these sophisticated azimuthal correlations, maybe it'd be nice to see what the cross section is and see whether they agree with your prediction.
Yeah.
They have data. There is data as a function of jet energy.
And one of the problems is that
It agrees too well.
one of
It agrees too well.
It's a long story.
One of the problems is that what the Castor measures and reports is jet energy. They don't actually give you the spectrum as a function of heat. No. They give you a spectrum as a function of jet energy, and then somehow the angular resolution, they know where the detector is, but within the detector, the angular resolution is not good enough to really, for some reason, they don't really get you to translate that into a PT spectrum.
They just
So they don't have rapidity separation, so it's integrated over the whole rapidity range.
Yeah, but then Al is completely right. I think the giant jets, so the sum and the difference, they don't have PT resolution to do the QT in the sense.
But
They have nothing. They can slightly nothing rapidity.
don't they have rapidity just because they have angle?
Well, the only angle they know is where the detector is, basically.
But they only
So-
know
so-
the jet.
Yeah, so
They know that the total rapidity is in this range.
Yeah, but
Well,
it depends to -2.
Yeah,
So
so-
No, but that's why
so
so if they're going to call 3 GeV here, so they're going to have very good angular resolution.
they don't. They cannot
They
take
don't. So they're not going to measure jets at 3 GeV.
well, they measure jets,
Integrated over.
which is integrated over some PT range, which corresponds to the integral of. So they measure jets as a function of energy, jet energy.
Yeah, but that's not interesting.
Which is
Look,
PT.
but that
So basically, they have no resolution in PT because they have no resolution in rapidity.
which means they have no resolution in angle.
They
But if they don't have good resolution in angle, this is a hopeless thing.
have a symbol. They can measure.
I don't know as well. It's just the theta angle. To get just to look, if they
Yeah, but
don't
then
have
you're
good
just
resolution,
convoluting
they
your-
don't measure the meta. If they don't have good resolution in theta,
Yeah, I mean,
they
it basically
can't
just means
cover
that the
the jet.
rapidity and the PT integrals are somehow tied to each other.
They measure anything 360 degrees.
Oh, but that's really bad. That's really bad.
I mean, look, let's see what they can measure. I mean, okay, I mean, Christoph, look, I mean, I'm working with one of the Castor guys on this stuff, and he tells me they can measure this. I don't know how they want to do this, but okay. I mean, maybe they can, maybe they can't, right? I mean, it's really,
Okay.
this is not on us to judge, right?
No, we don't blame you for that.
What exactly can they measure?
So, I mean, Christoph tells me they can measure jets, PT larger than 3 GeV, integrated over this skin.
But the question is, can they measure the PT?
No, but they can say PT was larger than 3 GeV, PT was larger than 5 GeV, something like that. So to that extent, apparently they can do it. This is what they say they can do as cuts.
Okay, yeah, it depends.
Right?
Okay, set energy gives you the lower limit for the PT.
Now the cuts, I mean, the cuts may be tied with rapidity. I mean, PT cuts may be tied with rapidity cuts and so forth. But okay,
See,
I mean, this one has to figure out. But okay, I mean, this is.
If they really could do
I mean,
a jet greater than 3 GeV and a jet greater than 4 GeV, you could take a differential and you could find the jet of 3.5 GeV. So it's a question of can they really do that? Because it's the same. If you can measure the total jet cross section above 3 and above 4 and above 5. Then you
Then you have a differential.
It's the same issue, but to do that, you really have to know your angular resolution.
Okay, good. So anyway, right? I mean, we'll see, right? They're working.
Yeah,
I mean, they're working on this stuff. There'll be stuff coming out. It's great to see that other people are thinking.
It's just that this is so revolutionary that I mean, it's super revolutionary, and one doesn't want to take it just as face value.
So I'm a little worried how many customers do.
A few more.
So now you can start. He's the bureaucrat right here, right? Beginning time.
Yes, I'm the bureaucrat. This is my bureau.
No, I should be. I mean, in the good tradition of things, I should be finished by half past or something.
Yeah.
Right. Okay. Good. So okay. So now okay. So this is okay. So all good, right? So now we're moving on to somehow the full calculate. I mean, so really trying to evaluate this full CGC. And I think this is actually interesting for a number of reasons, right? I mean, of course, first of all, we can kind of check all these various approximations people do in these calculations if we actually evaluate the full thing.
So the curves on the previous slide were just MV, or was it MV plus evolution?
No, it was MV geometric scaling in this TMD
geometric scaling.
factorization.
That's right. Sorry.
Geometric scaling.
So
That's how I did.
Evolution.
Yes, yes.
Okay.
And that's I mean. If you're going to do anything of what I'm going to start to discuss now, you're going to have to use something like geometric scaling. Because there's simply no other ways to do the residual numerical calculations and all these guys. Okay, so now I want to address some of the direct evaluation of this actual CGC cross section, right? And so this is interesting not only to check approximation, but also to somehow connect this with somehow the saturation models that we actually use in heavy ion physics, also, right? Where oftentimes we don't write down and say something, okay, our dipole scattering amplitude is now this or this, right? But really these models are kind of, in a sense, defined by, somehow having statistical ensembles of Wilson lines, right? Which have all kinds of nice structures, naturally include things like impact parameter dependence and so forth, right? So these are kind of snapshots of how the color field of the nucleus looks like, right? And so, I mean, one of the things that this could be interesting to look at also is that, essentially you have impact parameter dependence, right? You naturally know what somehow the saturation scale of the nucleus is in terms of saturation scale of the proton and where you hit here, right? Because, I mean, okay, this is just defined by stacking basically a bunch of protons behind each other and kind of adding their fields, right? Okay, so how are we going to do this, right? And so, if you look back at this cross-section formula, this was here, right? Looks very complicated, lots of integrals and so forth, right? So let's first remind ourselves actually how this is done to say compute single inclusive particle production, right? So say we compute single inclusive particle production, right? Then the cross-section is basically proportional to Fourier transform of the dipole scattering amplitude, right? And so how do we do this? Well, okay, we somehow have statistical ensemble of Wilson lines discretized with some spatial lattice here, right? But then when we actually go and calculate the cross-section, really, we don't go and calculate the cross-section directly, right? But what we actually do is we calculate somehow the scattering amplitude, which is actually just the Fourier transform of a single Wilson line, right? Then we square it, average it, and calculate the cross-section, right? So, okay, in this spirit, right, the same thing one should do.
There is no assumption about translational invariance.
In this case, there is actually. So if you don't have translation invariance, I think you still actually, I don't remember exactly how I did it. I think most of the time you still kind of do something like this.
You cannot even.
You can do it like this. It's still, I think it's still beneficial actually to do it. So.
No, I'm just saying that this approach does not rely on translation.
But
This approach doesn't rely on that. Okay.
I mean, it's always easier to compute the matrix element in squares rather than computing directly in square of the matrix.
So why is that?
Because
it seems like the first formula has one Fourier transform, and now you kind of.
Yeah, but okay, I would have to somehow tabulate the 2-point function first, or something like this, right? Whereas, so you have to tabulate the yeah. Yeah, so that's where like, okay, now I take all possible 2 points, right? Here I just take each point once, and
So basically,
it's just an easier calculation.
It's not only an integral over x minus y, it's an integral over x plus y.
Yes.
And somehow the doing the Fourier transform first, and then squaring lets you get the integral of x over x plus y for free.
Right. Okay, so
it's just writing it instead of d to x
You also
minus
have
y, d to
independent
x plus y.
Yeah,
is d to x, d to y.
yeah. But so I mean, it's
Yeah, exactly.
Right.
X d2y, that's 2 integrals, easier to do one integral and then square.
Okay.
that's the whole story, right? So okay, I mean, in the same spirit, right? We go back to the digest production at leading order, right? Okay, take out all the boring up factors and whatnot here, right? And just write it as a matrix element squared, right? Okay, so then basically, okay, matrix element squared is not very complicated, right? It's just it's possibility that the quark scatters or that the quark Luhmann projectile scatters. Basically, there's a splitting function, right? Okay, fine. Now, in principle, okay. So again, you can write this down, right? 2-dimensional integrals. Actually, again, easier to do this in practice in Fourier space. And so there's actually really only one subtlety, which is related to the fact that if you have this non-iconal splitting, right, then somehow the coordinate of your parent quark system, right, is not necessarily on a point on the lattice. So in coordinate space, this seems simple, right? So okay, so say your quark would hit here, and your quark gluon would hit here, and the quark gluon, depending on z, could hit somehow here. And okay, if you do this in coordinate space, you would just kind of interpolate here and so forth, right? This is fine. The thing is, you cannot do this in coordinate space. This is too expensive to do in principle somehow. So you do it in momentum space, and okay, you still get this kind of factor z here, but okay, you have to now be very careful with what momentum you actually assign to this on the lattice. So this is somehow a technicality, but this took me probably 3 days or 4 days to actually understand what was going on here. Yeah, but then other than that, in principle, there's nothing difficult here, right? I mean, you just have to basically look at the scattering of the normal quark, right? You look at the scattering of the quark Luhmann projectile. There's a 1-dimensional integral associated with that, and it's fine, right? You can go.
2-dimensional, right? What did you say? 1-dimensional.
Yeah, okay. 1 integral. Yes. It's a 2-dimensional. Fine.
So it's a very flat thing.
Okay, but you can go and evaluate it, right? And so, okay, I went ahead and did this, right? And so this is not looking at the cross section; it's just looking at the square of the matrix element, which essentially has all the interesting things, right? So okay, so for convenience here, what I did is I picked some momenta, right? So this is the momenta of the it's K here. K is the I think is the quark, huh? Let's have it.
Yes, K is 1. Q is 1.
Okay, good. If you say so. Okay, it doesn't matter. So I think K is the quark. So the quark is so back to the quark would be kind of in this peak over here, right? And so okay, so I mean of course you produce a lot of stuff at very soft momenta, so you kind of take into account for that. Okay, I've multiplied here by kt squared and qt squared, which is roughly the single inclusive cross section. And so indeed, I mean you see you get kind of nice back-to-back peak with some broadening in here, right? So okay, so this is in principle what you get out. Now maybe a little more intuitive is to actually, so this is for momenta around the saturation scale. So this is kind of like root 2 times the saturation scale. Is the momentum of the quark jet. What is maybe a little more interesting is to compare this to essentially the dilute limit of this matrix element, right? Because that kind of immediately tells you how important is actually multiple scattering here, and then actually the detailed color structure of this thing, right? And so if you take that
uncorrelated at the center, right? This is dilute uncorrelated.
Yes.
What do you mean by uncorrelated? Yeah, so basically what you do is you take the
and correlated.
Yeah, so basically what you do is you take this, I mean, you expand all the Wilson lines to leading order in the color field, and you keep up to quadratic.
It's automatic correlated.
So sorry, I probably missed it. Your ensemble is Jimborg involved?
No, this is just LV.
This is just.
I mean, doing the same on Jimborg is the same calculation as in. So everything that I show for MV can be the same way done for Jimborg. I just didn't do it. Okay, good. So if you take the ratio to dilute, then you typically what you find here is okay. You find an enhancement around. So if your momenta on the order of the saturation scale, enhancement around kind of factor 1 to 3 or something like this over here. I mean, you see points are still all over the map. I mean, one needs more statistics here and so forth to do this. But okay, so I mean, this is just a proof of principle that this can be done, right? And so another good cross-check is that if you now go to high momentum, right? So if you actually go to the dilute limit, right? So you know, multiple scattering shouldn't be so important, right? So this is now looking at kind of quark jets with a higher momentum. Then okay, I mean the gluon is still dominantly back to back. You still have some kind of angular distribution, but now you're much closer somehow in general to the dilute limit, right? So if you compare this here, this factors 3 to 5, and this is most of this is kind of on the order 1 with statistical fluctuations around it. It's a kind of slight enhancement. So okay, so this is. So we can, I mean, of course, so far I just did a single calculation here, right? But so in addition to comparing this somehow to the dilute limit, right? One should now also go compare this to TMD factorized form and so forth, right? So this can be compared to a lot of things and actually go and check it. The challenge here is, of course, right? I mean, this is, if you look at the number of points you get here for this cross section, it's not really very satisfactory, right? I mean, you'd like to somehow zoom in much more into this peak and so forth, right? But okay, I mean, this is what you have when you do this on the lattice. Right? So when someone has to find a strategy to kind of, I don't know, put more points in different regions and then kind of bunch different simulations together. This is why I think this will be relatively impractical if you want to do phenomenology with this, but I think it'll still be good to actually do it once and kind of see what the different things come out to be, right? But so yeah, I mean, what I find nice here is that you really see that non-linearities matter. Okay, good. So now, very last topic I want to address, and this is actually the most interesting case, right? So far, what we've been discussing is essentially the case where somehow we have these two forward dijets, right? But they essentially produce at similar rapidities, right? And so what that means is that if I look at this dijet system, right, there's really no large phase space for somehow having possibility of extra gluon emissions in between these dijets or so, right? And so in that case, I'm just in the standard CGC framework, right? And so one builds the cross sections out of this out of an ensemble of Wilson lines and correlation functions of Wilson lines. Now, of course, the more interesting case is if, and as I argued, this is something you can potentially look at the LHC, is if you actually start to open up the rapidity gap between these two dijets, right? And you essentially, or then open up the phase space for having extra, if you want to, BFKL-like emissions in between the two dijets, right? And so, I mean, this is interesting for a number of reasons, right? So first of all, I mean, if you want to look at angular decorrelation or so, then of course this BFKL-like dynamics gives you additional source of angular decorrelation, right? But it's also very interesting from some of the point of view of nonlinear evolution itself, right? Because that, unlike in the BFKL or so, I mean, these gluons that are emitted in between here, right? They also somehow strongly interact with the target color fields, right? And so that really, if you want to probe nonlinear evolution directly, right? This is a straightforward thing to say, right? Now, the thing is that, of course, it becomes now very, very complicated to somehow think of the cross sections because, okay, I mean, the gluon at a different rapidity will somehow see the color field of the target in a different way, right? And so instead of having this usual idea that somehow our CDC cross sections only depend on Wilson lines at a single rapidity, right? They will now depend essentially at the color field at the rapidity of the parent, right? Of the other daughter, right? As well as on the evolution that happens in between, right?
But you're still sticking to hybrid factorization?
No? I think so, because one of your jets is at the top of the diet.
But how do you know this jet is exactly from the bottom?
No, you won't have, this won't be the correlation limit because there's too many radiations in here. So you don't want to use.
I'm not gonna stick to the correlation limit. But I stick to
projectile size.
Projectile is equal.
So it's a hybrid.
It's a Guacamole PDF.
Yeah, so it's a hybrid.
So it's a hybrid. That's it.
So it's a quadruple.
Yeah, so I stick to hybrid factorization, but I just have a very complicated formula for the cross section. Well, actually, this is not my idea, right? And credit should be given here to the guys who worked out how to do something like this, right? And so this was kind of this was addressed by Edmond and Dionysus, right? And so, I mean, the challenge in a sense in this calculation is, right, is, okay, I mean, how do you account for the fact that you somehow have this rapidity gap in between the two, right? And so how do you actually write down the cross section?
But it's not a gap.
No, it's not a gap. No, sorry, I'm always saying gap. Yeah, I'm always saying gap when I actually mean.
different, but I also use gap.
Yeah, always.
It's a gap that's filled up, right?
Yeah, it's and so okay, so basically what they came up with is that the appropriate way to kind of formulate this formulate the cross section in this case is that you essentially, okay, so you kind of have the scattering of your parent projectile at the finite rapidity, which you express in the usual way in terms of that's just dipole scattering amplitude, right? But then basically the scattering of this additional additional emitted gluon, right, is constructed, if you want to first in a formal way, by the action of a Lie derivative, which basically produces this additional gluon on the color field of the target at the lower rapidity scale. So basically, the way the cross section then looks like is to say you focus on the part that gives you the amplitude, right? So you have the original Wilson line factor, which is the quark in the amplitude, right? Which scatters at some rapidity y, right? And then on top of that, you produce an extra gluon at some given transverse momentum, but at a smaller rapidity y naught, right? And so that's expressed by the action of this Lie.
So you're taking Nogent and expanding to do some kind of other step by step.
Pretty much, that's going to be what kind? I mean, wait a couple of slides. Okay, good. So this is interesting for a number of reasons, right? Because you really start to think about, somehow the way we think about evolution also a little bit different, right? Usually we build our cross section out of these Wilson lines, right? But now we have additional objects appearing, right? Which is somehow, so the way I've written this Lie derivative is we kind of say Lie derivative acting after some rapidity separation is the same as Lie derivative acting without separation times a propagator, right? So in addition, the new ingredient that kind of appears with this rapidity gaps is, if you want to, this propagator of how the additional gluon propagates. Well, I mean, you can see it as, depending on whether you see it as projectile target evolution, but propagates with the rapidity separation. Okay, good. Okay, so I mean, of course, right? I mean, of course, if you take this, right, and you close the gap and you close the field gap, right? So you reduce this to 0, right? You can recover the usual thing that you get from CRL. So you do this here, the soft splitting limit. Okay, so this is boring, right? But so now, how does one account for the evolution, right? And so, okay, so this is leading order Jibwork, right? So we can think of this as both projectile or target evolution. These two viewpoints are equivalent, right? And so, if you think about it from the viewpoint of projectile evolution, right, then somehow you end up with graphs like this, right? And so basically the fact that you have to account for is that now the additional gluon that you measure here does not necessarily come from your quark parent, which is also a gluon here, but can be emitted from essentially any of the stuff that has happened in between, right? So that's maybe sort of the more transparent thing to think about. But if you now want to instead think of this as evolution up from the nucleus, right? Then essentially what you have to do is, in addition to somehow caring for your inclusive color field of the target shock wave, right? You have to account not only for that, but you also have to account for essentially the inclusive gluon field plus an additional gluon in there, which you require to be present at the original rapidity scale. And so either way you see it, right? It will be accounted for by this Green's function. Yes.
So can I ask a naive question?
Yes.
So one can do something similar to what IK had done for the other problem, right? So you can solve this problem analytically first.
No.
Yes, you can.
It's a different evolution.
Before you ask, let me say
I
something.
didn't say anything about
Yuri.
Can I?
This is exactly, if you go at large and see, what we have done is exactly equivalent to what you did with Jamal in the paper around 2004. So this is just a complete different reformulation of that.
No, I understand.
So, but you remember the equations that you had, right? So I don't know how simple it can be.
Right. So, but one can do then the same magic, take those objects, right, in terms of Wilson lines, evaluate them in the MV case, do the Gaussian.
No, you have two evolution equations which are, I mean, nobody has able to solve them.
No, the equations one can solve, but presumably, I don't know, I haven't done it, but one can probably write them in terms of nowadays Wilson line language.
Yeah, I don't think so, because whatever he was doing, whatever they have calculated so far, it was locally wide. You always have correlators which are locally wide. The equations that you wrote with Jamal, you cannot express the solution in terms of something which is locally wide.
No, it's not local and wide. Of course, it's not. But you can try
but that's the
what we are doing now. But
so in the MV model, what we did with Jamal has a very well defined.
But then you have no
answer, no evolution, right? But then you sit down and think, and maybe you
no, but that's
I mean, what you could in principle do, right?
And you will repeat it. Otherwise,
well, that was our whole point as well. That's why the equations were so complicated. But okay, anyway, I mean, I haven't done it, but my feeling is probably the same mock-up could be done there.
This looks exactly with what you did, but it's significantly more complicated than
I
know it's about mock-up.
It's not a standard GMOC. It's a different version of GMOC. It's what we're going to speak about.
Okay, let me flesh how it works, and then we can then we can discuss it more. I mean, you could think. I think you could think of doing something like that, basically using your guys', or let's say BFK-like equations for the propagator, and then do
so there was a paper actually Jamal and I wrote right here at the INT in 2003 or 2004 when we considered production of two gluons, but they were separated from in rapidity. And unlike your case, which is actually simpler, none of them was in the projectile. So we had a hard projectile which we didn't tag on, and we were looking at production of two gluons. Now, I'm pretty sure the machinery we've used there could be applied to.
Oh yeah, sure. I mean,
give a simple result.
No, I mean,
now, of course, Denise is saying correctly that our answer was like we had like several ugly evolution equations which look just scary and no one evaluated them.
Yeah.
But nonetheless, maybe one can do some mock up along the lines of what.
But what we're doing now is going to solve that by GMOC, by line geometry.
So let me.
Is it really easier?
Yes. Yes, it is.
Okay.
So this is how it works, right? So okay, so in practice, if you actually do the evolution, it's a lot easier. At least I find it easier to think about this kind of target evolution, right? And so, okay, in principle, what you have to, the objects you now have to involve are the Wilson lines plus the Wilson lines plus an extra gluon, essentially, right? So the Wilson lines, I mean, okay, in the language of GMOC, right, they satisfy kind of these ordinary stochastic Langevin equation, right? For this is just stochastic form of GMOC, right? And so the extra gluon, right, basically describes the action of a derivative on these Wilson lines, right? And so basically satisfies in quote-unquote linearized GMOC evolution, right? Because you're basically just looking on what that one extra gluon that was there did, right? Which I wrote down here. You can write this in many different forms, all of which are equivalent for kind of small step size, right? But so okay, so I mean basically there's somehow color rotation and some kind of emission term, if you want. So, okay, and so the point is that the evolution between essentially, I mean, of course, right? I mean, the gluon, the Wilson line itself, plus the Wilson line and the extra gluon, right? I mean, they're the objects evolving in the same cascade, right? And so when I write something like this, right, then the noise terms here corresponding to the various real and virtual emissions, as well as the Wilson lines, right? They're identical between the two evolution equations on a kind of configuration by configuration basis, right? And so really somehow the new object that appears here, as I said, is kind of this Green's function or this propagator, which describes somehow the action of the Lie derivative after some evolution, right? And so basically this is basically our saturation analog of something like the BFK Green's function. If you were to square this, you should actually just get the BFK Green's function for the extra extra gluon emissions in between. I mean, this is the equations that you have.
Is that obvious that it has to be?
Yeah,
Yeah, because you're just putting one extra gluon, essentially, right? And you're acting with a derivative, right? You want to know the action of a derivative,
it is the
right? So how do you take a derivative, right? You kind of do it. So infinitesimal variation, right? I mean,
the question.
Why is the evolution?
No, Yuri. What is it? No, look at the Wilson line. It's non-linear in the background.
yeah, it's not linear in the background field, but it's linear in the propagate.
Look at the question for the above the question. It's linear in V, right? It's V on the left, V on the right. So it's linear in the Wilson line. The second question is again.
Then identifying it with DFT functions.
No. Come on. Look at the above. That Wilson line, that's GMO, right? GMO is non-linear in the background
Right.
field.
So why are you arguing with me? I'm saying what.
No, I'm saying is if you take
It's linear in
this.
G.
Yeah, if you take this and you were to remove the rescatter, if you were to try and
If you linearize it, then it's
yes. No, I'm saying is if you take the evolution equation,
I think we should argue that point out.
right. Seriously,
No, I think what the extra thing that you say is the following. If you try, you first solve the above.
Yeah.
You have V everywhere. So you see it is non-linear in V because you have it in the exponent. So long as you have determined V, then when you try to go and determine G, this is linear in G, okay?
Yes.
So you have two quantities that you have to evaluate. This is the point. You have the Wilson line and the charge of the Wilson line. So the V is non-linear. The second equation involves, if you have two parameters in the problem, G and V. Two things to calculate.
Yes.
So the second equation, of course, is non-linear in V, but it's linear in G, okay?
Yeah.
So that's,
I mean, the problem is
I don't know if
actually
it's a big deal,
analogous.
but just look at it, okay?
Yeah.
So that's all.
So it's another. Yuri, let me say
It's
something.
linear in G, but
It's analogous to computing a retarded propagator in a non-linearly evolving background field. That's actually
We
what
need
you
a
do.
growing strong background field. So G depends more on the V is anyway in the exponent.
Okay, so if you actually had solved the problem exactly first, well, my way.
Unit is equivalent to your way, so always keep that in
Right.
mind, okay? So it's shouldn't be
So if
different.
it's equivalent to our way, this is an important point in the following sense, that if you have a diagram, and I'm going to talk about two-gluon production, right? So if you have, okay, this is your projectile. If you have a diagram where you produce, say, one of your gluons up here. So I'm not producing anything in a projectile, right? And then you have, and I'm trying to remember, so bear with me. And then you have evolution like this, and then all of a sudden you choose to produce one of these guys as your second gluon. So your cut kind of goes like that. If you show this diagram to somebody like, well, this is all just a target, like Genia or maybe L, they would say, oh, this is 0 by AGK cutting rules. It should be 0. But what we saw with Jamal, I believe, if I remember right, that this thing actually doesn't disappear. So that's also already kind of, so what I'm talking about, right, this is a evolution between the two gluons with a non-linearity, right? As opposed to a simple linear evolution where you produce both gluons from.
So independent of the IGK argument that I don't understand, doesn't matter. The triple common vector is telling what you say, of course. It comes from the Wilson line. There's nothing to do.
No. Well,
sure. I can promise you that. So the non-linearity you mentioned that the triple common vector, of course, is that. Let me show the triple common vector.
Can I make a statement? Hold on. Before you wrestle the child.
That's the triple common vector. The V in the West is the exponent.
Right. So what's interesting here is that
Is the argument now that you have something which is non-zero for linear evolution, and then if you have non-linear evolution, suddenly becomes 0 because of AGK.
So right. So for instance, if you are producing a single gluon and you don't use hybrid formulae, but you really have a gluon at mid-rapidity, like this. So for instance, you can have a diagram like that, right? You have some non-linearity between the gluon you produce and the target, right? And you can have whatever cut you want. So this is a completely legitimate diagram. But then you say, oh, why can't I produce the gluon instead of this linear evolution here? Why can't I produce it there? And so if you actually do the calculation for this process carefully, it turns out that this contribution actually vanishes. So this, I forgot whether it's zero identical or cancel. Well, it's canceled by other cuts in AJK language. I don't know. In our language, it's canceled by some real Gaussian cancellation. So
Thomas, what it's saying is that before you put the nonlinearity in, you have a cut over a single ladder. Then AKG says with a single particle measurement, the Pomeroy loops go back.
Yeah.
They don't change that original number.
all fans, Pomeroy fans.
Yeah, there can be fan diagrams or even loops.
It's the same logic. It doesn't matter. Right. So AJK seems to work for a single gluon production, but here somehow it doesn't work. So it's
I have no idea, but that's not if it's there, right?
No. Ultimately, if you just want to plug and chug, plug it in the computer, it doesn't matter. In terms of understanding what goes on the
I don't know.
So somehow I think that actually the way the problem is set up here is that the two particles that you're producing is one from here.
Oh, yeah.
And then this one.
No, not necessarily.
I mean, principally, it doesn't matter. I mean,
doesn't
change
matter,
the vertex of Kalman.
Just take this guy, carry it into the projectile.
Exactly.
Everything I said here.
So Thomas, if you that the first particle it's an incoming one for simplicity, but the second one can be anywhere.
I mean, the point is, it's on the way I understand it's basically that, okay, I mean, say you produce two particles anywhere, right? You have to basically account for the scattering of the first particle, you have to do this evolution in between, and then you have to scatter the second part.
Exactly. But
That's with y0, y2, y0, y0, something like this.
But in the way
But you have this thing which usually, I mean, in BFK physics is the BFK Green's function. In our case, it's just more complex.
Exactly, but because you're applying all that on an S matrix for dipole to start with, it means that you measure automatically the quark that was incoming, and then you measure a gluon anyway.
Yeah, sure. Yeah, but you could produce the first one out of
something else.
This doesn't matter.
As you remember, if you want to emit really good gluons like Yuri was suggesting, then it becomes intrinsically more complicated because each time you have to follow now another charge in the equation line.
Right.
Yeah. So you will have to follow the evolution of three objects. So that's why we chose this simple example where you measure the quark plus one gluon, but this gluon, I mean, it's
Can be anywhere. Many funds and measure a gluon just below.
So what's the point?
I'm saying that it is a little, at least in the way we try to solve the problem, it was much easier. I mean, not in terms of formalism. You can do the formalism to emit two gluons. It is simpler in terms of practice to measure, let's say, the quark in the top or the dipole or whatever one of the legs plus one gluon.
That's not what I'm saying. All I was asking about and all I'm saying now is that, as I said, from what I remember from what we did with Jamal, I think if I were to tackle your problem, I would get exactly the same object. We had this object M, which depends on those three coordinates.
Yes.
And so you'll have it too. And that's the object which describes the evolution from here down to this guy. Sure. And that object did have nonlinear pieces which didn't cancel and therefore violate AJK.
Let me interrupt you. In the appendix of our paper, you find your equation derived from our format.
I'm not, yeah,
So
I'm just making, I'm sorry, I think we're again in violent agreement. All I'm making is an observation that in this formalism, just like in the formalism Jamal and I had, there are nonlinearities in the evolution between those two gluons. And well, again, I said to you it seems like a trivial statement, but there are situations where similar nonlinearities like this between the projectile and the gluon you produce actually cancel. So it's not such
they
a
make
trivial
us here also too for some reason, but I don't know. That's probably was the solution.
Yeah, but you want to say that if you linearize that thing or you use it in its full glory, it gives the same result.
No, I don't. They don't cancel here. I would
triple Pomeroy vertex means nonlinear. What the heck there? Otherwise, we just BFK letter.
Okay.
So we tried finding, no, they don't cancel at the same level. So for single gluon, basically, Kirill, I guess, and I saw that back then that they disappear explicitly. And at the same level of the same differential or similar differential equations for the two gluon production, those things don't vanish.
But you see, single gluon plus quark, right? You don't mean only just single gluon. I mean, here we're talking about single gluon plus two particles. That's a big difference.
Again, what I'm trying to say, there are two different problems. If you're interested in producing one gluon, which is not exactly what is being done here, I understand.
Okay.
I understand. In this problem, AKG works. And you have, even though you don't assume the evolution between the projectile and the gluon to be linear, nonlinearities go away. Here, is a two-gluon production that I'm talking about, but I believe it's similar in for this quark plus gluon production that Soren is talking about. The evolution between the two gluons, of course, is not assumed to be nonlinear, and it seems like nonlinearities don't cancel. So that's the essential difference. AKG doesn't work. AKG breaks down. And this is sort of a non-trivial observation. That's all I'm making. I'm not accusing anyone of doing anything wrong. Okay? Breaks down. That's all. Let's move on.
Good. Let's move on. Okay. Good. So the point basically being, right, is to now. Okay. So now to build your cross section, right, you need the width and lines, and you need these quote unquote propagators, right, in the background of the color field, right. And so picture is you start them at some initial rapidity scales where basically it just locally produces a gluon, right, and then you have evolution equations, coupled evolution equations for both of them, kind of evolving them up to the rapidity of the parent quark. Numerically, this is still very complicated. So this in principle is all that more understood, right? So it took me some time to realize here, but this is what really then actually makes it possible to evaluate is that actually when you start with evolution down here, right, you can already specify the momentum of the gluon that you measure at the end of the day, right? And so instead of keeping somehow track of some bilocal object at the end of the day, which tells you to measure gluons in each point in space and time, right? And you say I measure a gluon with a certain momentum, you have to deal with a much smaller object. Since the evolution equation is linear in this propagator, right? The Green's function to produce a gluon with a given momentum is the same. The evolution equation for the Green's function to produce a gluon with a definite momentum is the same as the evolution equation for the Green's function to produce a gluon at a definite position. So nothing changes over there. And actually also the evaluation of the cross section becomes a whole lot simpler, right? Then you have, the cross section is basically just given by essentially tracing out the square product or squaring the matrix element involving the scattering of the original projectile and this Green's function to produce this evolved Green's function to produce the gluon. Okay, good. So then you can go ahead, code this all up, and then start to see what this looks like. And so this is still very complicated. So what I did so far was just a simple proof of principle calculation. So there's a lot of color algebra involved somehow in evaluating all these commutators and so forth, right? So I hate to do this, so I just did it for SU2, where it's a whole lot simpler, right? But okay, so the physics should be pretty much the same, right? So unfortunately, I did this a year ago, and then kind of stopped doing this. So I don't actually remember what the exact one. I got carried away by other interesting stuff, right? This is why I said this was extremely useful for me to give this talk to actually rediscover all the interesting things I did, right? So I cannot tell you what the kinematics of the dijet pair here was, right? But I can certainly tell you that I did evolution, right? Okay, and so
what's on the axis?
So what's on the axis is this is essentially the dijet spectrum. So as a function of the relative azimuth length. Right? And so you see, okay, if you don't have any evolution, right, you have this kind of nice back-to-back peak over here, right? I wouldn't focus too much here on the near side. So this, it seems to be there's some kind of enhancement here too, but this could be finite volume effect, or I don't know. I have to look at this more carefully. Yeah? But so the point is focus here on this west side peak, right? So without evolution, you have a nice kind of back-to-back peak up to of course the intrinsic transverse momentum, right? So this was the kind of the physics we were talking about before, the sort of 2s squared decorrelation you get over there, right? And then you evolve, right? And so I have this here for evolving, the alpha bar delta y1 unit of rapidity. You already see, okay, somehow the back-to-back nature of this correlation has already started to significantly deplete, right? And then if you go to, if you do this for 2 units of rapidity, essentially,
So CERN has done elaborate phenomenological studies of these two jets. Now, of course, they're in the region where the jets are greater than 50 GeV, so probably the background MV doesn't make very much of a difference. But they've done elaborate analysis of this.
No, this is also. Look. These are going to be momenta on the order of a few times saturation scale.
But
so, right? So this is this.
You can't measure that at CERN. Now you've got a rapidity gap. You're going to have to get away from the very edge where Castor is. They can't even measure 50 GeV well. How are you going to get down to a few GeV?
Look, I mean, I just.
They'll set a new record.
Yeah.
No, look, I've been fighting with Mike, I've been pounding on Brian Cole for a long time. He said maybe they'll get down to 50 GeV in the future. 4 GeV? Come on.
No, look, I mean, it's a. Well, I mean, we can try to do the calculation for higher momentum, I mean, but then
The
doesn't make
background
a
isn't
lot.
going to matter.
Yes,
It's
I
going to
agree.
be the standard calculations that have been done to higher orders now. Look,
Fine, but
Samuel Wallone and colleagues have done higher order calculations in these 2-jet measurements. There's been elaborate fits to discern data at the level of 50 GeV and above. To see the, and that's certainly not nonlinear at 50 GeV.
Sure.
So you're going to get into the nonlinear regime, or you said better way, to get into the region where the saturation momentum makes a difference. You're going to have to get into a region which, it's really very exciting that maybe in the true forward region, Castor somehow can measure this, and the background is for some reason much less. But we know as you go away from that forward region, the background is overwhelming, and they have no hope of getting down.
yeah, no, sure. I mean, you see, look, I'm aware of it.
Yes, that's more promising because Rick, especially with SV mix, is going to do good jet measurements. The backgrounds are much less. Of course, the saturation is a little bit less too, but it's more hopeful.
No, but I mean, this is, I mean, to tell you, I mean, look, this is a calculation. I mean, this kind of calculation you're never going to be able to do for phenomenology anyway, right? I mean, this is too complicated. I mean, you cannot actually produce enough data to actually calculate the cross section. I find this interesting to just see what actually happens. I mean, there's interesting nonlinear evolution effects really between the two.
Why is there a data limitation?
No, the problem is this. I mean, this is just an expensive calculation.
Well, the last
This is just an expensive calculation, and I cannot possibly do it to the level of sophistication that I can actually go and predict the cross section with this, right? But I can look on the theory side on what actually happens, and so for instance, it would be interesting to compare this, say, against having just BFKL-like emissions in between also, and see, what is the effect of nonlinear evolution, or things like this, right? So this is really the aim here.
As a theoretical laboratory.
Yeah.
I agree. And for and then as a theorist, you can go down to lower transverse momentum, and you can see the effect from BFKL to the non-linear things. And I said that's amusing. I don't think that has a future in experimental connection. Maybe at Rick, but
why not linear hadrons? Why does one need jets specifically? I mean, I understand fragmentation, but spoil.
Yeah, in principle, it's.
I think it's probably better with hadrons. Yes.
Yeah, but we can also grab it.
Then you can go lower.
But okay, I mean, first of all, we have to find something interesting, right? I mean, if we can say, okay, look, I mean, this, to me, this would be very interesting if you see a difference between now having nonlinear evolution in between or having linear evolution for instance. Right? And this would be maybe one of the. I mean, that would be.
That's very effective.
Yeah, I didn't understand.
No, I can explain later because we're kind of done. But
yeah, I mean, this is my last slide actually.
Sorry, Jimlock is fixed coupling, all right?
This is fixed coupling, Jimlock.
So that's also not good for phenomenology.
That's also not good. Yeah, I mean, you would have to dial down the evolution speed at the very least. Yeah, but yeah, I mean, this is to explore what actually happens once you open up the gap, right? It's overall looks physical, but okay, I mean, it's still interesting. I mean, you still have to do some cross checks, and in particular, it would be interesting to compare this against sort of various levels of essentially simpler models for the cross section. Okay, so yeah, this is it, right? So doing here, I mean, looking at dijets, right? And have a few preliminary results, so stay tuned for more. Thanks.
Anyone still has any questions? What are you guys fishing? Not looking out the window.
Yeah.
Not for conveners. Questions, anyone? If not, let's meet maybe at 11:05.